Powerful collaborations, cutting-edge science, and curious minds coming together for a glimpse of the future. Stay tuned as we look at the latest updates on some of the most promising technology projects. In this episode, the M3TERA project, now in completion. What does this mean for you, and what's next? Today we are speaking with Franz Dielacher and Chiara Mariotti about a project called M3TERA, which has recently wrapped up. In this project, they attempt to advance the commercialization of terahertz frequency devices by finding ways to make things smaller, more efficient, and less expensive. Let's just jump right into this. We'll start with you, Chiara. Why are you interested in this project?
I did my PhD in millimeter wave technologies. I was trying new technologies for higher frequencies, and so I was already related to this world. And then afterwards, I joined Infineon, and with Franz, I was involved in this project to connect what's the millimeter wave or RF world to the process development world. And so I think it was a very good fit because I was already doing that in the PhD now with kind of passion.
And if somebody walked up to you on the street and said, what is terahertz wave or technology, what would you say?
So imagine that now we are using for our connectivity and wireless transmission lower frequencies like 2.4 gigahertz normally, or other bandwidths very low in the frequency range. Now we want to push our frequency band up, beyond the 100 gigahertz. And the reason for that is that we want higher connectivity, higher capabilities of the network, faster communication in the wireless, in the air. And so to make possible this to happen,
Okay, so everyone wants faster communication,
exactly.
And this is what this promises.
We want to download our stuff from the cloud very fast, and this is one of the ways that will enable this in the future.
And what would some other uses of this technology be?
I would say here, indeed, like Chiara already mentioned, there is this trend from the gigahertz into the tens or even hundreds of gigahertz and to the terahertz here. And there is a good reason for that. On one hand, there are very practical reasons. For example, in telecommunications, we need bandwidth. There is a huge hunger of additional bandwidth. And here, indeed, because of the significantly increased amount of data in the network, right, and which has to be transported. And there is just not enough bandwidth available at the lower frequencies, and that is, of course, the reason for the push into the beyond 100 gigahertz now. And beyond of that, the other area is indeed that when we go into beyond the 100 gigahertz, it is opening up a new interesting applications, which we are not possible in the, let's say, below 10 or below 100 gigahertz area. These examples here are, for example, when we talk about radar. Radar is an important issue in automotive. Today it is 77 gigahertz used in the radar, but in the future it should be beyond 100 gigahertz, and this has the advantage that you have a much better resolution and finally can also use it then finally for example, road surface detection. The car should smell itself if there is an ice on the road. Or another application could be security scanners. On the airport, everyone is very unhappy to go through these security checks. And with this new kind of, terahertz capabilities, finally, maybe walk-through machines will be there that you even don't need to stop, just go, right? And interesting aspects in this context. Another interesting aspect is, food is also an issue, and food quality control. And with spectroscopy in this kind of high frequencies, we can imagine to be even able to do food quality control with this kind of technology. And so there are a lot of exciting areas and interest behind here. Or astronomy, right? Weather forecasts and radio astronomy. It's another interesting area, space observation, where you also need this kind of towards the terahertz frequencies.
Are you saying there's a chance in the future that the weather could be correct?
It's already not so bad, right? They have already a lot of nice tools and setups in place, and they can predict already very properly how the weather on the next day will be, right? But on the other hand, of course, we want to further improve. And another issue is, of course, the climate change and this kind of stuff. We can imagine that this will be possible with this kind of new technologies.
So it sounds to me like we have many uses for this cool stuff. So what's standing in the way at this point? What's the roadblock?
I would say it's always the issue, of course, how much does it cost, right?
Yeah,
and
exactly.
Finally, in a way, this kind of terahertz frequencies, they are already in use today, but the equipment is very expensive, and that more or less restricts it to more or less the sensitive area, military applications, or space astronomy is also a kind of professional sensitive applications where somehow just for a few machines the money can be invested to build it. And of course, now with our technology, we hope that this will finally lead to a significant reduction in price and make this kind of new capabilities affordable really for the commercial market. And this is a most important issue in this context.
And it seems to me like this was the heart of this project. I couldn't read much about this without running across this phrase over and over again, a micromachined heterogeneous integration platform. This seems to be the key. What does this mean, Chiara?
The point is that up to now, at these frequencies, as Franz mentioned, we have very sophisticated, very costly systems, bulky, heavy, and everything. And this is not producible in a fab like in Infineon, for instance, and for high volumes for these other applications that we mentioned before. And the idea is to use micromachining to make it possible. And I mean, from the technical point of view, this is the solution to shrink the system from something very bulky, heavy, and big and costly to something very small, like what we have in our mobile phone. Think about something like that. So a chip where everything is integrated inside. And this is the goal of the project.
And this way, when it's small, then it's manufacturable, the cost goes down, you can make millions of them.
And the size and the weight is much lower. Yeah.
Good point. And so your charge in this project was to make a prototype. Is that correct?
That is very true indeed. And when we say to demonstrate the feasibility with a prototype, here the first focus is on a telecom application. Namely, here we have this kind of high-speed data links in place already today, but some in the frequency range is 70 gigahertz, 80 gigahertz, and in the future it should be 145 gigahertz and even beyond 200 gigahertz. And so our demonstrator will be a high-speed data link at 145 gigahertz, built with all the components we are researching or more or less developing in this project. And then beyond of that, there is also a secondary application, and there it's about sensing. Mm-hmm. And an interesting area for the sensing, for example, is also in the car context, again, in-cabin monitoring. The car, when we go towards the automated driving, it will be important to watch if the people in the car, what they are doing, if they are sleeping or watching a movie on their smartphone or whatever, right? And this kind of in-car radios will be able to observe all that. And beyond of that, also if an accident happens, for example, if you have to ignite the airbag, then you have to steer the airbag into a critical direction and protect for example, the heads of the people in the car and not the feet, right? And all this will become possible with this kind of new technology.
Amazing.
And the secondary application is exactly to study how to use this technology in-car, in-cabin monitoring.
Okay. So these are some really great examples of this technology being used. Do you foresee this happening?
I think so. For example, in the car context, you may have heard the story from Uber, right? There was an accident and there was still a person in the car to take care, and it finally was proven that this person was watching a video instead of observing what happens on the street, right? And of course, so in the future, to really have recorded what's happening in the car will maybe also will be an issue for the insurance, right? And so very interesting aspects in this whole context.
Okay, very interesting. And what would be some of the drawbacks? I mean, we've talked about the good sides of this technology. Are there any bad sides that we see?
It takes a long time to get it into a production, let's say. Yeah. But that is normal, right? With these kind of high-tech things, it is a very long phase of research required until you have it in a status that you can ramp up a volume production. That takes, let's say, something in between 5 and 10 years or 10 years or even more, right? And of course, this is one of the bad sides, that it will take time until it will be affordable and accessible for everyone.
Also, the quality check that must be, I mean, there are very high requirements, especially when you go into the car. The quality is relevant. So until you get in the standards, it takes time.
How about drawbacks as far as being dangerous? We talk about cancer screening, for example, and people think MRI and they think X-ray, and then they start to think about that there might be health risks. Is this different?
Indeed, in a way. I mean, it's a very good question, by the way, right? And I just remember a few years ago, we have built a person scanner, a first one already for airports. By the way, it's in place. When you go to Munich, to the airport, you can already experience it. And that is 70 to 80 gigahertz. And we had to go through all the approvals. And indeed, there was also a concern regarding the radiation, right? And finally, we were able to prove that the radiation is much less than in a mobile phone. And the mobile phone you have close to your head, but this screening wall you have 1 meter away from you, right? And so for the human, the radiation effect is zero. They just said, yes, go ahead, no problem.
So as far as the project goes, it's done, right? Or almost done. You're have a meeting next week where you present results, I'm assuming. And so how do you feel about the project?
I would say overall the project went very well. Of course, we had some issues, in the production. Not everyone was to the point in the first trial, but finally we have managed. And this final review meeting will be on Wednesday, Thursday this week. And we just got the information from the system house who has built this telecom demonstrator that everything is ready and up and running. 10 gigahertz link over 145 gigahertz carrier frequency. And so we are very happy and will be able, hopefully, to fulfill the expectations from our reviewers, right? Yeah. And make them happy as well.
That's great.
We will see the wireless transmission of this very high frequency, so gigabit per second running from the transmitter to the receiver.
And you will actually show this, right?
There will be a demonstrator.
So what happens next? Is there another project similar to this that you are going to embark on?
Indeed, in a way, we have luck. Namely, there is a perspective for a continuation here, and really to dig deeper into the applications in the car context, namely for short-range automotive radars suited for road surface detection, and beyond of that also of in-cabin monitoring. And beyond of that, of course, we do not want to give up this idea to use it, for example, for food quality control. And in this context, also more research is required, and we are not really there yet. We do not have all the pieces together for these other applications yet.
Okay, so Chiara, the food monitoring, this is an interesting aspect. Can you tell us just briefly how that works?
That's, a good question, because, this was developed by one of our partner, that is CSCM in Neuchâtel in Switzerland. And the idea is to send a signal at these frequencies they did a demonstration with some chocolate, with some metal inside, or some something inside, and then when you receive the signal back, you can recognize that there is something in the chocolate pieces, and this is how it works basically. But of course, it's a quite complex system.
Okay. And are there other projects going on that are similar to yours that maybe support you in a way, or is there information sharing, or is your research proprietary and just for you? Can you leverage other people's technology?
It's a very complex area we are discussing here. And on one hand, we have to develop or to further develop the respective or appropriate production technology. And then beyond of that, we have to develop the components for this certain application here, right? And when it comes to the production technology here in our company, we have flagged as we have this kind of silicon germanium technology, which is suited to be pushed and to make it suited for these very high frequencies. Namely, it's a silicon technology. That means it's cheap in the production. And here, as a kind of important parameter, we are talking about the maximum frequency you can achieve with this kind of process. And there we are at 700 gigahertz already today. And when you compare this with CMOS, it's definitely double the frequency already, because with the CMOS we are at 300 gigahertz. And with the silicon germanium, we already simulations and calculations very nicely show and prove that we can push it towards beyond 1 terahertz. And then there are even 2 terahertz is reachable with this kind of technology. And then there are, of course, other also competing technologies on the market here, like indium phosphide. But when we talk about indium phosphide, it's much more expensive in the production. And as our focus is here really on the commercial volume market, of course, it's important to have the right, also price-wise, the right technology in place. And beyond of that, of course, we need this MEMS platform. And here, of course, what we are using in the demonstrators now was quite a long-lasting process at our research partner in Sweden to produce these parts. And of course, for a volume, we would need to implement and to transfer this technology into an industrial production. And that is, of course, also a huge complex effort. And beyond of that, of course, on the products themselves, the development, we are at the beginning.
Can you tell us your partners in this project, the people that you worked with?
Yeah, of course, our coordinator, most important, Technikon, of course. Then we have KTH in Stockholm, and their focus is exactly on this kind of MEMS technology development. Then Infineon is contributing with the semiconductor transceivers in this silicon germanium technology. And beyond of that, we already have started to experiment to produce this kind of MEMS in our facility and to take advantage from what more or less from the research at KTH. And then, of course, the system partner here is Ericsson, and they are also building now the telecom demonstrator. We will see in a few days, right, in our final review meeting. Then, of course, when you talk about wireless communications, antenna is an important piece, right? And so we also need antennas, yes. And for that we have Antaral in Spain, who are contributing with this kind of terahertz antennas. And then we have Chalmers University. They are very well known for all their microwave and into the terahertz knowledge and research. And they have developed the circuits we are using here in the Infineon technology. And so also, of course, a very important contribution from them. And then we have this CSM at Neuchâtel in Switzerland, and they are contributing with the secondary application, with the secondary demonstrator, namely to explore these high-frequency waves for example, in-cabin monitoring. And other things like just mentioned by Chiara, they have started to experiment also to use these frequencies for food quality control.
On behalf of Technicon, I want to say thank you for your contributions to this project. Thank you for doing what you're doing in science to make our tomorrow a better and safer place. And just wanted to see if there's anything else you wanted to add about the project.
Of course, we could continue to discuss, but maybe it's appropriate. We could, for example, go, of course, into further industrial applications, but maybe it's for the time being enough what we already discussed, right?
So thank you for your contributions again, and we look forward to seeing the exciting things that come out of this project.
We also look forward.
Yes, indeed. That I can confirm.
Yeah. So waiting for the final meeting.
Thank you so much. This podcast has been brought to you by Technicon. The project leading to this application has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 644039. This work was supported by the Swiss State Secretariat for Education, Research, and Innovation under contract number 15.0059. The opinions expressed and arguments employed herein do not necessarily reflect the official views of the Swiss government.